Solving for light chain gene combinations is the number of V segments times the number of J segments, and you get the little SpongeBob. Solving for heavy chain gene combinations is the number of V segments times the number of D segments times the number of J segments, and you get the little more buffer SpongeBob. Solving for the number of random combinations of heavy and light chains, which is the sum of light chain combinations and heavy chain combinations multiplied, you get the ripped SpongeBob.
The antibody diversity, heavy and light chain pairing.
So here we have table 6.1, which shows all of the ways that we combine the heavy and light chains and each segment present on those, which is indicated by the V, D, and J. And it shows the number of different segments, which you multiply to get all of the different possibilities. And recombination between these three segments is required to encode the variable region of the heavy chain of the Ig molecules, and then a combination between the V and J regions encodes the light chain molecule.
So these high numbers of specific segments allow for numerous possible combinations of the gene segments, and antibody constant regions determine heavy chain class and effector functions, which contribute to diversity.
Antibody genes in mature B cells, the large numbers of possible recombinations contributes to the antigen binding specificity. Recombination between the V region segments results in increased diversity as well. And then here on the bottom, we have a link to a fun little internet game that can be played to help further understanding of this concept.
Heavy and light, heavy and light. I gotta have me my heavy and light. The mu, the delta, the kappa or lambda. You get more diversity using the gamma. Nachos and lemon heads on my dad's boat. All these different antibodies will cure your sore throat. We sail around the world going port to port to make the whole antibody long and short. Put on your life vest.
Welcome to the show. Today we'll be talking about
of the hairpin by Artemis, resulting in overhangs, and addition of P nucleotides by DNA repair enzymes.
So first, Artemis is gonna walk over to the two hairpins and cleave them. This will then bring over the nucleotides to both the 5' ends. So we have two 5' overhangs. Now our buddy, DNA repair enzyme, is gonna come and add the complementary DNA strand to both of these.
Which are the P nucleotides.
Project, we are doing exonuclease trimming. And what exonuclease trimming is results in the loss of nucleotides on one or both strands of the coding region of the hairpin structure.
Where are nucleotides in the coding joint?
Oh no, exonuclease.
Exonuclease, oh god.
Oh, our friend.
Who are you?
I'm just a random nucleotide.
Yay.